So I don't need to do that myself. So just to give you a sort of brief overview of what it will say here. I know that most people here are not emulator guys, so I will give a quick emulator primer. You're compiler guys, so you will actually recognize quite a lot of stuff that's going on with emulators. Then I will go into T-EMU 2 and the history, the architecture, and how we use TableGen and LLVM in the emulator. And then some future directions and some sort of final remarks of how we have used LLVM and what issues we ran into and so on. So, what's an emulator? Well, normally with a software-based emulator, we say that it's an instruction-level simulator. And you're executing an emulated target's instruction set on a virtual machine running on some host computer. The emulator needs to simulate memory as well, including a memory management unit, depending on whether your simulated processor has one. You need to simulate peripheral devices, and you need some way to integrate these into the instruction set simulator. You can do this by having some external device models or an interface for them, or you can have them completely tied into the emulation core. And when we do emulators, we usually measure performance in MIPS, and that's millions of emulated instructions per second. The benchmark is usually running Drystone for when you test for integer performance, and that's really confusing because Drystone also reports a MIPS number, which is completely different and has nothing to do with this. Anyway, so what do you have in an instruction set translator? Well, you have an instruction decoder. You might actually need several ones. So you might have one for an interpreter. There might be one for if you also have a binary translator integrated into the system. And you might have an assembler and disassembler. And for this, you also need to have some instruction decoders and encoders. Now, in addition to the decoders, you need some type of instruction semantics. So usually you have one type of routine per instruction, and but you might have different variants. So in the Spark architecture, which is used in the European space industry, you have a special register 0, which is hardwired to 0, and you might have special variants of instructions when they write to 0 because you're not using the result. So you can speed certain things up a bit. Another problem, or one thing that you might think of is that if you have an interpreter and a binary translator, they might have different types of instruction descriptions or how to describe the semantics. So how do we deal with that? Well, you can write 2. If you want to have both systems in the same emulator. But I mean, rather not. You have a bug in one of these and you're trying to maintain them. I mean, it's a nightmare, right? Or you write 1 and then you just hash if-def yourself around all the issues that you encounter. Or you can use LLVM and you write 1 and then you transform it to whatever relevant format you have in there. So, an instruction set simulator, there are usually 2 types. There's interpreters and there are binary translators. So, usually with an interpreter, you might see that this is familiar from compilers and in sort of programming languages. We have a decode dispatch interpreter. This is the simplest type. And basically, in an emulator, you have a loop. You call a function, fetch something from emulated memory, you get an instruction. You decode it, you get the pointer to a function, you call that function and passing along the processor and memory state. Right, so very simple. Of course, this doesn't actually run very efficiently. So usually what you do is that you bake everything into one function in the end, and then you have what's called a threaded interpreter Anyone who doesn't know what a threaded interpreter is? Everyone knows what a threaded interpreter is? Okay, there's some quantum state as usual of knowledge and no knowledge. Right, so with a threaded interpreter we embed the main loop in all these instruction implementations. So the fetch and the decode is sort of put into the footers of each instruction, and you jump directly to the next instruction. Sort of like doing a tail call, but you stay usually within one function, and you just jump to do a computed go-to and jump to a label. Now, if you go to binary translated emulator, I mean, it's roughly the same thing as a jitter. Similar optimizations apply, and there you translate a block of code of the target code into native host code on the fly. You execute this, and then hopefully it runs faster. Well, it should run faster because you don't have to do the decode and fetch stage for every instruction anymore. You can combine these with interpreters. You might know that some JavaScript engines does the same thing. They do interpretation. If it runs too slowly, they switch to another mode, and then so on. There's a notion in emulators called basic block. It's not related to LLVM basic block, but it's related to the basic blocks of the target instructions. And in a binary translator, you can chain basic blocks together, and that's roughly equivalent to threading in interpreted emulator. So, how do you implement this? Well, I mean, you can have a C function that just emits function code directly. You cannot do much optimization this way. You can do register allocation and proper instruction selection, like doing shifts instead of divides and stuff like that. It's very fast at code generation time, but the code it generates is of course not the most efficient. Another way is to have a data-driven approach where basically you have some intermediate representation that emits that you transforms to a machine code after various transformations. For example, LLVM. Emulators are often implemented in assembler, C, or custom languages. Assembler is nice because you can fine-tune it, and in an emulator you're counting instructions. So to simulate an add instruction on a Spark, you need to fetch two virtual registers, you need to add them together, you need to store the results. So the fewer instructions that you can have from this, the faster your code will be. So you can fine-tune assembler quite well, it's really nice, but it's not portable, as we all know. C is another option. It's really nice for writing a dynamic code generator, but it's really tricky to start writing threaded instruction set translators in C because they become unmaintainable in the end. So what a lot of people do is that they use a custom language or a domain-specific language, and you get the portability, so you need to maintain your language, but you get quite high performance, it's easy to maintain the emulator, and so on. And for T-EMU 2, our emulator, we use the LLVM toolchain. So we use TableGen and LLVM assembler. I suspect that we have one of the larger LLVM assembler written programs on the planet, but it's anyway. So what's the state of the art with emulators now? Well, we have a bunch of binary translator systems. For example, there's one called OVP Sim. You have Wind River Symix, and you have Q-EMU. Q-EMU is partially GPL, and that's a problem in certain industries, especially when you need to integrate the emulator into the simulator. And it might not be controlled by the company writing the simulator, but by requirements further up in the chain. So it can be tricky. Interpreters, there are plenty of these. In our case, we have a Spark simulator, and in that we basically have one called T-Sim, which is from CPU manufacturers. It runs around 60 MIPS. And we have the ESOC emulator, which is the property of the European Space Agency. It runs a bit faster unless you turn on the MMU, in which case it just loses performance. Now we also have T-EMU 2.0. I'll show you the performance figures later on. And then there's all these game console emulators and stuff like that that we might have played with at home or. Right. So now to the main, the interesting part here for me is T-EMU 2, and it's a successor to T-EMU 1. So T-EMU 1 was a derivation of the ESOC emulator, and it formed the baseline actually for work on the next generation ESOC emulator. It's written in something called EMMA, or the Extensible Meta Macro Assembler. It's a nice name, right? And it's an embedded assembler which uses Ada as a host language. So it's sort of like target independent or architecture independent. So you can write a new backend and so on. The reason it's written like this is that in the old days, the ESOC emulator was written in VMS assembler, in a macro assembler, and sort of kept on evolving from that. And this emulates some US military standard processors that have been used in, for example, the Rosetta mission lately, and the Spark V8 architecture. Now T-EMU 2, however, is a complete rewrite, and it's written in C++11 and LLVM assembler. It's interpreted, but it's prepared so we can sort of go to binary translation fairly easily. And we spent a lot of effort trying to get some device modeling APIs that are actually reasonably powerful and easy to use. And we can emulate multi-core processors, which is in the space sector, which is quite conservative. That's sort of what's being looked at the moment. It's multi-core processors, and we'll probably get these within 10 years. And they will clock at an amazing 300 or 400 megahertz and being quad-core. But at the moment we emulate Spark V8 only. It was written as a set of libraries, so you can hook it up in a simulator, and we have a public and stable C API. And there's a command line interface. Right. So it's divided into two parts. You have an emulator core, which is the Instruction Set Translator. And that's written in TableGen and LLVM assembler. And basically what we get is, I'll show you the sort of the steps later on, but what we get is we get a decode dispatch interpreter that we automatically convert to a threaded interpreter using LLVM. And we use TableGen. So TableGen is a nice LLVM tool, which is part of the. Has anyone used TableGen here? Okay, good, excellent. Now, so we use TableGen to describe all the instructions, and also the instruction semantics is embedded in these. So it's a bit the duplication of some parts of the LLVM compiler toolchain, but we wanted to have our own part that we could maintain offline, basically. And then we also have a shell, which is outside the core, and that's basically the public programming interface for the emulator core. So I mentioned also that you need to do memory emulation. When you have an MMU in the system, if you need to do basically a table walk for every memory access, it will be really, 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 really slow. So what we implement is basically a sort of a software TLB in the emulator. So you have a cache, you look at the virtual address, you check if it's a hit, and in that case you load directly. And if it's not a hit, you go out to an external memory system, and then you can, for example, check for whether breakpoints have been set and do all kinds of stuff like that that would consume a lot of time. And then you make sure that you only cache RAM and ROM and stuff that has no breakpoints, for example. And we have support for different types of memory attributes like breakpoints, we have watch points. There's two very space-specific attributes called upset and faulty, which means upset is a sort of single event upset, it's a bit flip. And faulty is something which has multiple event upset, so it's non-correctable. And you need to simulate this in order to test space software. Right. For the MMIO system, it's based on interfaces, and you basically implement a struct, fill it with function pointers for fetch, read, and write. You take a transaction object, which is filled in with virtual and physical address and so on. And all this needs to be simulated to have a representative system. So our compilation pipeline then. Well, we have our table gen file, this spark.td. It's loaded by the program Imogen, the emulator generator. And from this we get an LLVM assembler file which contains the emulator core, and we get the disassembler and an assembler. Then we take this LLVM assembler file, we load it in opt, and we transform this using some custom magic, and we get our threaded core. And of course that's bitcode because that's what operates are by default. And then we just compile everything and link it together into a shared object. So conceptually not too strange, I hope. Like I said, you need a decoder. So we can actually generate multiple decoders based on our table gen format. So we can have switch-based decoders, basically nested switch statement. We can make nested tables, or we can make a single unified table. It all depends on what you need. And the nice thing is that you can just quickly experiment. You can generate different decoders and see which one is actually the fastest or most efficient or for the specific task. Right. So we're really happy with using table gen for this. So for the decode, excuse me. So after we have generated our main assembly file, I mentioned that we transform this, and I'll give you some more specific examples after this slide. But basically, it's fairly easy to generate this single function with a threaded interpreter in there, and I'll show you how it can be done. We also use something which we call Emulator Intrinsic, so we have special magic functions, and that makes all the instruction definitions actually sort of, they make them data structure independent in the end, so we can play around with the virtual machine state objects and reorganize fields and so on. We can also easily change the way that we access registers, because it might be that different methods of accessing register state is different depending on if you're an interpreter or a binary translator. So this is what it looks like. There's some duplication because we're describing the same instructions as done in the LLVM sources. But basically we use these multi-classes, and we can define a register immediate and register instructions in the same go. And we basically define the instructions, we give them opcodes, the assembler name, and the semantics in LLVM assembler, and then there's some concatenation of this, and basically you get something that hopefully works after this. So, what happens then? Well, we run the Imogen tool and we get hundreds of functions that looks like this. So we have an unpack block which decodes the instructions on the variables in the instructions. So you have, for example, the registers. The registers are variables in the encoded instruction. They're not something that you can sort of call a specific functional. You can in certain cases, but in principle it's unpractical. So you get the register identifiers, and then we have the instruction semantics, so we load the registers, we add the registers together, and then we store the result in the machine state object, and then we're done with this function. So now we transform this into a decode, or to a threaded core, and then we end up something like this. So we have this one emulate function, and it's a bit simplified because there's a lot more code than this, because it updates counters and timers and whatever. But basically, I have an entry, it loads the current instruction based on what's pointed out by the program counter of the simulated processor. And then we do an indirect branch to the destination. In this case, say we have an add register instruction. We basically populate it with 5 nodes to pick out the different, to pick the instruction. And then we call this function that was generated earlier, this add RR. We just call it directly, and then we increment the program counter, we fetch and decode the next instruction, and then do a new indirect branch. I mean, this is a bit simplified, so if you have complaints, it's already solved probably. And of course, we will not keep this add RR function there because we inline all that code using LLVM. So, what do you think, what kind of performance we can expect from this? Well, if you write an emulator the bad way, which is basically with single functions, you end up with probably 10 MIPS. This is not super fast. If you consider that a modern processor runs at 3 GIPS or something like that. But after we have transformed the emulator core and optimized everything, this is what we get, and we still interpret it though, but on a modern machine we're basically, compared to our competition that we know about, we're about 50% faster. One nice thing is that we don't have any slowdowns for having an MMU in the system, and with the ESOC emulator you drop down to 25 MIPS, so that's already a big difference. I don't know what the numbers for TSIM are because it's a quite expensive software product, so I'm just taking the numbers from that they have published by themselves. I should say that anything above 50 MIPS is pretty good for an instruction set, for an interpreted emulator. So, where are we moving from this? Well, we are moving towards binary translation, and we are also looking into different architectures. I mean, it depends on the needs of customers, of course. We want to have some way to model devices in different languages and frameworks. For example, it would be nice to connect the system C model directly, or to integrate the VHDL model directly. Another standard or device modeling standard that exists is something called SMP2, and that's used by the European space industry. And if you want to have something sold in the European space industry, you need to support this. It's just general law. And we're looking into making bigger model libraries. So now we had 3 different Leon processors, which are the current Spark processors used by the European Space Agency. And there was an older processor called the ERC32. But all these are still used. I mentioned, Rosetta that landed on a comet just recently, or the lander. And it had been flying for 10 or 15 years already. You know, and some missions have been up for 15 years, and they're like looking into having them running for another 10 years maybe. And that gives you sort of a nice perspective of on software maintainability, especially for the simulators. Anyhow, I mentioned binary translation, and we're moving there. And basically, since we have all the instructions in LLVM assembler, I mean, they're already binary translation friendly, because you have the machine code jitter, for example, but they're already binary translation friendly. We can also easily generate decoders which are just tailored for the binary translators, so the instruction decoders, which is quite nice. And we can also we can also generate different types of binary translators. Some of this means that you're generating x86 code directly, so it will not be portable, but the framework will be at least. For example, we can transform the LLVM assembler to a code, to just code that emits the assembler for each instruction directly. Another way would be to generate something that's position independent, and you just stitch together blocks with memcopy. It's a bit tricky to stitch them together because you need to sort of match up registers and stuff like that between the blocks, but it could be an option. Another option for doing binary translation this way is to use LLVM IO directly and use the LLVM JIT, like for example the MC jitter infrastructure. You can probably use it. I'm not really sure how easy it will be yet, because MC jitter is really for compiling a language which consists of well-defined functions and so on, and we don't really have that in this case. So we would need to define something like an extended basic block in the emulator, which we can probably form as the strongly connected component, which terminates with all indirect and absolute branches. So if you call a function, if you have a call instruction to an absolute address, that's the end of your basic block. But probably we actually want to do some combination of this. So last year, I think it was in the news that the WebKit JavaScript engine got a LLVM as a jitter stage, and it turns out that the WebKit JavaScript engine, it first does interpretation. If that runs too slow, it switches to another mode and does some type of interpretation of pre-compiled code. And after that, it switches over and does binary translation, or real jitting. And after that, it even goes into an LLVM-based jitter. So we know from practice that the MC JIT is not the most efficient thing. So we probably want to have some combination of this, and we can take some hints from WebKit in this case. Right. So what have we learned? We have some bumps on the road. Well, firstly, table gen. I mean, it's not like it's super well documented. I mean, you best figure it out by using it. I mean, the syntax is documented. It even has a nice grammar and everything. But the table gen API, when you write your table gen backend, it's a bit, you read the code and you try to figure it out. And if it doesn't work, you just keep banging on it until it does. And hopefully you've managed to get somewhere. Right. There's also a nice LLVM dev meeting tutorial. It's nice. You can watch it on, I think, YouTube, wherever it was. Another thing that we have encountered is that, well, LLVM assembler. Well, it wasn't really meant for our use case, but it is useful in our case. And is a bit hard to debug. There's no way to include files, which could be useful in our use case, but I mean, we just run things through M4 or the C preprocessor and that's solved. And also there's no way to define named constants. That's also solved by M4 and C preprocessor. Not on this slide is that there are no hexadecimal constants in LLVM assembler. And that's really annoying actually. But yeah, I realized this isn't really the intended use case of LLVM IR or the assembler, so I mean, we're not really super complaining about this. But yeah, as something that we had to deal with. So whenever we have a constant, there's always a comment saying that, oh, this is this in hex or binary. Not the nicest thing, but yeah. So to conclude here, basically find that LLVM is really nice to use in an emulator for two reasons. We have table gen, and we have the IR and all the transformation passes. So LLVM is not just useful for compilers and programming language developers, but it's useful also for a lot of other nice tools. And basically, we're able to do an interpreted emulator in a very little, in a very short time frame, which is still quite competitively, performs quite competitively. And we can guarantee that we can go to binary translation. And we just realized that if you start using LLVM, or maybe even on a higher level, and integrate that into your compilation pipeline of your program, you can do very powerful stuff. And I'm sure this is not just limited to an emulator. I think we have a quite unique use of LLVM. I'm not sure, but I would guess that we are one of the larger LLVM assembler programs written. So, yeah. There's also some related work. Some people have been using LLVM to optimize T-EMU. Yeah. So that concludes my talk. I hope there are nice, interesting questions.
So if I understand you correctly, the reason why you're not using the existing table files in the LLVM backend, also already described instructions, is it because you need to go back from the instruction to an LLVM IR semantics?
Yeah.
Even in those cases where sort of the other direction is, I mean, so the existing files basically have the other direction. We go from an LLVM selection tag to the instruction.
Yeah, exactly. So we need to do the reverse mapping. So I mean, we could have taken this and probably extended it, but then we would have basically needed to track whatever is done in the repositories. So it would be quite high on maintenance, I think. So we just wrote our own descriptions, and yeah, that's basically the reason. Yes.
Another question. If you want to do cycle accurate simulation?
Oh, that's an interesting question. We have a timing model which is sort of roughly accurate for targets which are not superscalar, lacks a TLB, and I mean, it's not perfect, right? But we have static instruction timing. There's also stuff that we ignore, pipeline-dependent behavior. For example, the Spark standard says that if you write to the processor state register, you should not do anything depending on that for 3 instructions. Okay, really, we don't care. If you do something like that, we will not catch that error. In my mind, we could probably add some sort of static code or machine code analysis to find these cases, but it's not interesting to simulate. We do have support for putting in cache models. That slows down the emulation quite a lot. But you can do this on a statistical level. The easiest way and to maintain the sort of the relatively high performance is to, if you're writing an embedded system software, you could run it in an accurate cache model, get statistics, and then plug it into the statistical model after that. And then, at least if you want to do this in what's called an operational simulator, which is what they use at the European Spatial Operations Center to hopefully test telecommands before they send them to the spacecraft, although that doesn't happen and there's been some mishaps. Will not name anyone. Cycle accuracy is hard. If you want to have it really cycle accurate, you need to do System C or VHDL. And then you're down at like 500 kips. Yeah.
All right, one question here. Your estimate of greater than 300 MIPS, is that just the performance of the translated code, or does that include the cost of the translation?
That's based, so that's the performance of the translated code, but I mean, it depends on what you're running. So if you run Brightstone for X iterations until it finishes, basically. And if you run it for enough iterations, the translation